Okay, in this exercise here, we have 6 different power series, and we have to calculate what is the convergence radius of this power series and specify the interval where they converge absolutely. Well, the interval where they converge absolutely is easy. It's just the absolute value smaller than the radius of convergence. So determining the radius of convergence automatically determines what is the radius, the interval of convergence. Okay, well, this is in the case where you have a power series in powers of x. If you have a power series in different in a different interval like this one, well, it's a different story, or like this one. Okay, in this case it would be x minus 2 smaller than rho, and that would be an interval rho minus, sorry, 2 minus rho, 2 plus rho. Okay, right. Well, we will talk about this in due in each of the exercises here. Okay, so let's do that, right? And in each case, we're going to use the appropriate method. So let's begin with the first. Remember, all the power series are like this. In general, they may begin at 0, right? But sometimes the first term is 0, so the first coefficient is 0, and they start at 1. Well, doesn't matter, right? It's one particular case of this. So in general, what you have is this, right? These are the power series. And if you have that, the definition of the radius of convergence is this. The limit when n goes to infinity of the n root of an in absolute value, okay? But if this, well, if the limit I'm going to write exists, so this can also be equal to the limit of the absolute value of an plus 1 over an. Remember, this is a consequence of the theorem of Stolz, right? That if you have this limit, then the limit of this root is equal to the limit of this, okay? So you can calculate the radius of convergence either using this formula or this formula here, the one you prefer, right? So it's up to you. Okay, well, let's begin with, well, let's try to use this whenever possible, okay, because it's easier. So actually the way we're going to use that is, if 1 over rho is equal to this limit, of course rho is equal to this limit, the limit when n goes to infinity of an over an plus 1. So let me just do the first, okay? And for this one, an is 1 over 2 to the n squared. So if we calculate this limit, so rho is going to be the limit when n goes to infinity, and you have 2 to the n squared in the denominator, right? Because this is an, and an plus 1, so is in the denominator, goes here to n plus 1 squared. Now you cancel 2 to the n with the power n, and then you have 2, right? And that is the limit when n goes to infinity of n plus 1 over n squared. And since the limit of this fraction is 1, this limit is 1, so the limit is 2. So the radius of convergence of this first series here is 2, okay? So, and the interval of absolute convergence is therefore minus 2, 2, okay? Let's go to the second, this one here. Here we have an equal to n factorial over n to the n, right? So the radius of convergence according to this is equal to n to the n over, sorry, n factorial over n to the n, and then n plus 1 to n plus 1 over n plus 1 factorial. All right? Okay. N factorial divided by n plus 1 factorial is just n plus 1 in the denominator. Okay, and if you have, well, let me write it. So n plus 1 here, and then here I have n to the n, and I simplify all these factors here, and then I just have one factor, the last one. But this and these are the same factor, so I just cancel the 1 here with this factor here. And now we have the same power, so we write this like this. Is n over n, which is 1, plus 1 over n, which is 1 over n, to the n. And this limit is e. So the radius of convergence of this series is e, and the interval of convergence, of absolute convergence, is this one, minus EE, right? Okay, the third one, AN is equal to 1 over n times 10 to the n minus 1, right? So this limit goes like this, is n here, 10 to the n minus 1. And here I have n plus 1, 10 to the n. Okay? Now 10 to the n minus 1 cancels with the exponent. The limit of this is 1, so this radius of convergence is 10, so this is minus 10, 10. Okay? So far so good, right? Let's go to this one, the fourth. For the fourth, I have an equal to 1 over the square root of n. And then the limit, the radius of convergence is 1 over the square root of n, and up here I have the square root of n plus 1, and this limit is 1, right? So 1 is the radius of convergence, and the limit, or the interval of absolute convergence is that one here. Okay, now I have this other one here, right? And for this one I have to do something slightly different. First, what I'm going to do is to rewrite this series like this. I'm going to write this series as the sum from n, where it doesn't start at 0. So from n0 to infinity of z to the power n. And z is going to be 3 minus 2x, which is the argument, right, that you have here in the series, okay? So this is a series, a power series in n, right? So the rate an here is equal to 1, and according to this calculation, the limit, the radius of convergence is of course 1, right? When you calculate the quotient of two consecutive terms, it's all terms are equal, because the sequence of the coefficients is constant, then the ratio is 1 and the radius of convergence is 1. So what I mean by this is that the convergence of this series is here. This is the region of convergence. But of course z is equal to this, so actually what I have here is 3 minus 2x smaller than rho, okay? Okay, or if you prefer, well, smaller than rho, smaller than 1, because rho is equal to 1. Actually, this is equal to 1, okay? But I can write this, or I can write this. Both are the same, because we're taking the absolute value, so it doesn't matter the sign of this expression, right? So let me choose this one. And this one, of course, corresponds to these two inequalities. If I add 3 to the whole expression, I have 3 minus 1 here, smaller than 2x, smaller than 3 plus 1. So 2 is smaller than 2x, which is smaller than 4. And if I divided this, then I get 1 smaller than x smaller than 2. So the interval of absolute convergence here is 1, 2. It's not a symmetric interval, of course, because the argument of the series is not x, is 3 minus 2x, right? So this is one way in which you can do this. It's not the only way. You can do this in an alternative way, which is more natural for or fit better in the arguments that we have made about the power series. So we can rewrite this as a power series of this form: an times x minus c to the power n when n goes from 0 to infinity. We can write it like this. Well, let me call it, well, actually, let me rewrite this. I'm going to write Cn to distinguish from this an, because this an is for this series. Okay, Cn is going to be different. And what we have here is c is x minus a to the power n. So we want to write it this like that. So if we wanted written like this. What we have to do here in this expression 3 minus 2x is to factor out the coefficient of the x, which is minus 2. So minus 2 multiplies to x minus 3 half, right? If you multiply this by this, you get minus 2x, and if you multiply this by that, you get 3, right? So this is equal to that. So if you substitute this here, what you have is this expression. You have sum from 0 to infinity minus 2 to the n, okay, and then x minus 3 half to the n. Now if you interpret this series this way, then you have a different coefficient. The coefficients are like this, minus 2 to the n. And if you want to calculate the radius of convergence, then you have to do this. You have to calculate the limit when n goes to infinity of the absolute value of Cn over the absolute value of Cn plus 1, right? And this is the absolute value of minus 2 is 2. So this is 2 to the n over 2 to the n plus 1, right? And you can cancel this factor with the power n, and the result is 1/2. So the radius of convergence of this series, which is the same series we're talking about, is 1/2. But that's not important. The important thing is where is the interval of convergence, of absolute convergence. And the interval of absolute convergence in this case will be the absolute value of x minus 3 half, right, which is the power that we have now here, is smaller than 1/2. This is what defines the interval of convergence. And let's see what this is, because this is equal to minus 1/2 is smaller than x minus 3 half, smaller than 1/2, right? And if I add 3 half to both sides, what I get is 3 half minus 1/2 is 1, smaller than x, smaller than 3 half plus 1/2 is 2. So the interval of absolute convergence is exactly the same one that I have obtained before, as it should be, right? I mean, the fact that we're calculating the radius of convergence, well, the interval of convergence with this procedure, I mean, changing it, making a change of variable, calculating the radius of convergence of this series, and then transforming it into the interval of convergence in the variable x is identical, right, to the one that we get through this procedure. I mean, the procedure is irrelevant, right? What is irrelevant is where does this series converge, and of course it has to be in the same region. So however you want to do this exercise, I mean, transforming the variable like here, right, and using what we know about this series, or writing the series in the standard way like this and calculating the radius with the standard procedure and getting the interval, what you get is always the same, right? So it doesn't matter how you do it. Okay, so this is the fifth exercise, and finally we have this one, so it's x minus 2 to the n divided by the square root of 2n, okay? Okay, check, yeah. All right, so here we have, this is written in the standard form, and the coefficient Cn, the Cn I'm talking about here, right, is equal to 1 over square root 2n. Okay, so calculating the radius of convergence is simply done like this, is Cn, so 1 over the square root of 2n divided by Cn plus 1, so square root of 2n plus 1 here. Well, the 2 cancels, and the limit is obviously 1. So the radius of convergence is 1. So the convergence of this series occurs in this region. And that means here, and if you add 2, what you get is 1 smaller than x smaller than 3. So the interval of absolute convergence is the interval 1, 3.